Hey everyone! Today, we're diving into one of the most fundamental tools in any statistician's toolkit, the one-sample t-test. You know that stuff in your study guide that can feel a little, well, dry? We're going to break it all down, step by step, into an explainer that actually makes sense. So let's kick things off with a question you've probably heard your whole life. We've all been told that 98.6 degrees Fahrenheit is normal human body temp. But is it really? I mean, how would you even know for sure? Well, instead of just taking someone's word for it, we can actually use data to get a real evidence-based answer. And the tool for this job? It's the t-test. It lets us put common knowledge, like this, on trial.
Okay, so here's our game plan. We're going to start with that big question, then we'll get into the t-test toolkit itself. We'll look at the two main ways to reach a conclusion, walk through a full example, and then wrap up with some common mistakes to watch out for. Let's get into it.
All right, let's open up that t-test toolkit. The specific tool we're using today is the one-sample t-test. Now, it's perfect for when you want to test a claim about a population's average. But, and this is super important, you don't know the standard deviation for the entire population. But hold on, before we can take off, we've got to do a quick pre-flight check. You can't just use this test on any old data. There are 3 requirements you have to meet. First, your data has to come from a random sample. Makes sense? Second, the population should be normally distributed. Or, if you don't know that, just make sure your sample size is at least 30. And finally, number 3, your sample can't be more than 5% of the total population. That just helps make sure your observations are independent. Okay, let's meet the key players in our formula. We've got X bar, which is just the average you calculated from your sample. Then there's mu naught, which is the number from the original claim you're testing. S is your sample's standard deviation. And of course, N is just your sample size. Simple enough. There's one more piece we need, and it's called degrees of freedom. Now, it sounds way more complicated than it is. For this test, the calculation is super simple. It's just your sample size, n minus 1. This little number is really important because it helps us pick the right t-distribution curve, which is how we figure out our probabilities. And here it is, the engine of the whole t-test. This formula takes all those ingredients we just talked about, mashes them together, and spits out our test statistic, a single number that tells us just how far away our sample evidence is from the original claim we're looking at. So, we've got our test statistic. Now what do we do with it? Well, that brings us right to our next section. Once you have that number, there are 2 main paths you can take to make your final decision. This slide lays out the 2 paths perfectly. Think of the classical approach like this. You draw a line in the sand, called a rejection region, and if your test statistic crosses that line, you reject the claim. The p-value approach is a little different. It calculates the probability of getting a result as extreme as yours. Even though they work differently, here's the key. Both paths are designed to lead you to the exact same conclusion. All right, now for the fun part. The theory is great and all, but let's make this real. We're going back to that body temperature question, and we're going to use some real data to walk through this whole thing, from start to finish. Here's the evidence. We took a random sample of 35 people. For that group, the average temperature was 98.2 degrees Fahrenheit with a standard deviation of 0.62. This is the data we're going to use to challenge that old 98.6 claim. First things first, in any hypothesis test, you have to state your hypotheses. The null hypothesis, or H0, is the status quo. It's the belief we're challenging. So in our case, it's that the average temperature is 98.6. The alternative hypothesis, H1, is what we actually think might be true, that the average temperature is just not 98.6. So we take our sample data, that 98.2 mean, the 0.62 standard deviation, and the sample size of 35, and we plug it all into that t-statistic formula we saw earlier. You run the numbers, and this is what you get. This single number, negative 3.8168, is our key piece of evidence. This is the smoking gun of our investigation. So, is our evidence strong enough? Let's check out the verdict. With the p-value approach, we get a p-value of 0.0007. That is tiny. It's way smaller than our usual cutoff of 0.05. And with the classical approach, our test statistic of negative 3.8168 falls way out in the rejection region. So both methods are screaming the same thing. We reject the null hypothesis. And this right here is how you'd state your finding in a research paper or for a class. It's the formal conclusion. Basically, it means our sample data gives us really strong evidence that the old belief about 98.6 degrees is probably wrong. So we've walked through how to do the test right. But before we finish up, let's cover our last section, a few common mistakes to avoid. If you keep these in mind, you'll be able to use this test with a ton of confidence. Here are the top 3 things to watch out for. First, always use the t-test, not the z-test when you don't know the population standard deviation. That's a big one. Second, always check your data for outliers. Just one crazy value can completely mess up your results. And third, double-check your degrees of freedom. It's an easy calculation, but it's also an easy and critical mistake to make. And there you have it. That's the one-sample t-test. It's a really powerful way to use a small sample to investigate a claim about a huge population. So I'll just leave you with this thought. Now that you know how to do this, what piece of common knowledge are you going to put to the test?